Hello, this is Greg Dorais, and I'm pleased to present to you an approach to permanently extend life beyond Earth by starting with an artificial gravity space settlement ground-analogue. This talk is about solving the gravity problem that has been preventing life from living in space for long durations. If you have wondered why people still aren't living in space beyond Earth's orbit, going to Mars, and so on, then you may find this talk of interest. This is the first step of a three-step plan to permanently extend life beyond Earth. The second step is to test a small-scale version of this modular artificial gravity facility in orbit. The third step is to build an orbiting full-scale version, one module at a time, that people, plants, and animals can live on indefinitely. I have served as an intelligent systems research scientist at the NASA Ames Research Center since 1997. At NASA, I participated in the Deep Space One spacecraft mission, the L-Cross Lunar Impactor mission, and the LADEE Lunar Orbiter mission. I was also the chief technologist and deputy program manager for the NASA Small Spacecraft Technology Program. This artificial gravity work is associated with my work in that program, where I worked on Step 2, that is, developing the technology for a 1/40th scale flight version of this concept, constructed out of small spacecraft called CubeSats. This is a recorded version of a talk that I gave at the 2016 AIAA Space Forum on Step 1, developing a full-scale space settlement artificial gravity ground-analogue. 4 years ago, Cassini took this image. It is extraordinary not because of Saturn's rings, but because of this pale blue dot that contains all known life in the universe. Life may be abundant throughout the universe, but as it stands now, this is it. Even after 55 years of space travel, no life that we know of has left Earth's orbit, and the life launched into orbit doesn't stay there long. Sooner or later, life needs to find a way to survive beyond Earth, or all known life will go extinct. There is a good chance humanity will survive this year, but several other species won't. And this is without a catastrophic extinction event, which could strike with little, if any, notice. So what do the experts say? A growing number are expressing grave concern. Professor Fenner, formerly with the World Health Organization leading the effort to eradicate smallpox, was pessimistic, and unfortunately is no longer with us, but I believe he may have underestimated the role technology can play in sparing humanity, as well as many other species. Stephen Hawking has also been expressing concern. However, he also may be too pessimistic in that it will take 100 years to develop self-sustaining space colonies. It seems to me that a concerted effort can accomplish it much sooner. Accomplishing this is what this talk is about. So why haven't we already done this? Why is it so hard? Actually, we have known at least some of the reasons for quite some time. Astronaut Scott Kelly, in testimony to Congress after completing 340 days in space, recently summarized the top 3 reasons why living in space is difficult for humans, even with regular supply ships bringing everything they need. These reasons are microgravity, the focus of this talk, radiation, which can be mitigated with mass and lots of it, and the atmosphere. There is no fresh air on spacecraft, but we can do something about that as well. It is NASA policy that flight crew health and safety is paramount. So if you ask, why are astronauts subject to these conditions, as Scott Kelly did, you'll get at least 3 answers depending on how you ask the question and who you ask. The first reason is that the trip to and from the space station has been far more dangerous than the issues of living on the station, resulting in a round-trip mortality rate of 1 to 2%. So the argument is, if you have the money to spend on making flight crew safer, you will get the best return on investment by making the launch and return trips safer. However, people will also be safer if they don't have to make the trip as often, which can be done if it is safer to live in space for long durations. The second reason is that although the radiation level is harmful, this is why flight crews don't go outside the Earth's magnetic field, which partially shields them from radiation, and flight crews are only permitted to stay in space for a few months. Since flight crews are not going to stay in space for long periods, then artificial gravity is not required. However, this argument is like saying, since the world is a dangerous place, just stay close to home. It is not a long-term solution. The third reason is somewhat counterintuitive and goes something like this. Increasing the level of spacecraft radiation shielding only moderately is actually more dangerous. The radiation particles in general, and galactic cosmic rays in particular, are traveling so fast that sometimes it is better just to let them continually pass through the flight crew and hope they don't do too much damage in the process, because if you try to stop them with shielding, but only manage to slow them down, the flight crew is bombarded by the original radiation and many more particles from the shielding particles energized by the radiation as it passes through the shield. For those familiar with the game of pool, an analogy is that a radiation particle hitting a shield acts like a cue ball hitting a rack set of balls, causing them all to scatter. The result is that if you're going to use shielding, use enough to stop the primary and secondary particles. We've been doing this on nuclear ships for decades, so we have the technology. It would mean a paradigm shift in how we build spacecraft for humans by making them less like aircraft and more like aircraft carriers with very thick hulls, and perhaps along with magnetic shielding like that provided by the Earth. Microgravity causes many negative effects in humans, which I'll discuss on the next slide. This is what medical experts are telling me, so you would think that these experts would be for artificial gravity for flight crews, but many of them oppose it. Their reasoning is also counterintuitive. As bad as microgravity is, radiation is worse. If artificial gravity is provided to the flight crew, they will stay in space longer, and the radiation will do more harm, so they are healthier without artificial gravity. My response to this argument is it too much to ask for both? We have the technology to engineer spacecraft to provide ample radiation shielding and artificial gravity so that the health and safety of people living in space is much greater than it has ever been. Before I present such a design concept, I'll explain the gravity issue in a little more detail so you can better understand the dangers of microgravity and the opportunities that engineering gravity present. It turns out that microgravity is harmful to most life, particularly humans. And the more we find out, the worse it is. This is a partial list of the negative effects microgravity has on humans. This alone is enough to prevent people from staying in space for more than a year. What are the multi-year effects of living in such an environment? We really don't know, but it doesn't appear to be good. What we do know is that changing gravity changes life. All known life is continually at 1G, except for a few short-term exceptions. Practically all life thrives in environments where temperature and precipitation vary. So what are the long-term effects of various and varying gravity levels on life? We really have no idea. We know that different life thrives in areas with different mean temperature and precipitation levels. These regions are called biomes. A few are depicted on this slide. Humans are at the top of the food chain, but we really don't know how many biomes, along with the species they consist of, need to indefinitely coexist on a space settlement in order for humans to be nutritionally self-sufficient, or just for these species to survive. This is a simplified version of a graph created by Professor Whitaker mapping biomes by mean temperature and precipitation. We find different species in the tundra, desert, and rainforests. We know that changing the environment changes the species that flourish there and how they evolve. This graph adds a third dimension depicting gravity to the biome graph. Note the blank regions above and below the 1G plane in the biome graph that depicts life on land. Many species could theoretically survive for at least short periods within most of the volume of this entire graph. But all life is currently confined to this 1G plane, with short-term exceptions. What sizes and kinds of biomes could robustly support humans at different mean gravity levels? How would they evolve? A long-term artificial gravity facility can help answer these questions. NASA has been studying life in centrifuges from the early 1960s, shown as a 20G centrifuge used at the NASA Ames Research Center. Typical runs subject humans to hypergravity for hours. Small centrifuges have subject small animals to hypergravity for a year without negative effects. However, to my knowledge, no human has been subject to hypergravity for more than a few weeks, and multi-generational studies of animals in hypergravity have not been done. With that said, for over 60 years, designs for artificial gravity space stations have been pitched to the U.S. government with no success. Back in the 1950s, Dr. Wernher von Braun proposed this artificial gravity space station to the U.S. Army as well as to the general public. Von Braun went on to be the first center director for the NASA Marshall Space Flight Center and led the development of the Saturn V that took people to the moon. He wanted this launch vehicle to be used to build this modular space station shown, but it didn't happen. However, this was designed to be a station and not a settlement. In 1975, a NASA study described the space settlement design shown. It was much larger than von Braun's design, and since it would be built from lunar raw materials, it would take quite a while before it would be habitable. Eventually, such a space settlement may be built, but the design I'm presenting today is larger than von Braun's in order to permanently support human life, but also is modular so that it could be habitable in less than 20 years. In order to address the artificial gravity challenge, I'm proposing an extended stay hypergravity test facility. This space settlement precursor is an extensible ground-based facility that produces an adjustable hypergravity environment in a 300-meter diameter facility. As I will show, the design is flexible, and a single module version can be implemented at a relatively low cost. There are many benefits a hypergravity test facility can offer. In this talk, I'll focus on validating artificial gravity designs on Earth as analogs for off-Earth settlements. But also can be used for therapeutic treatment for people that suffered from microgravity or other type of debilitating diseases, or simply as a physical therapy to improve health. The simplest version is a train-like rail car that runs on a banked circular track to produce the desired hypergravity. Depicted in this slide is a 3-car hypergravity vehicle with a transfer vehicle, which allows people in cargo to enter and exit the hypergravity vehicle without it changing velocity. This drawing is not to scale. This slide depicts the 4 major subsystems and their interfaces: the hypergravity vehicle, the transfer vehicle, the vehicle track, and the depot and control center. The hypergravity subsystem breaks down into cars where each car is an element. People in cargo can transfer between cars as permitted, as on a train. Each car consists of 3 elements: 1 or more cabins, a tilt mechanism, and a chassis. The chassis runs along a set of 4 tubular rails at a fixed bank. The tilt mechanism changes the cabin angle relative to the chassis according to the chassis velocity. So down is always straight down for the occupants, regardless of the velocity or gravity level. This image depicts the chassis at a 30-degree angle and the cabin tilted at an additional 30 degrees for a total tilt of 60 degrees at maximum velocity. When stopped, the cabin would be tilted in the opposite direction, negative 30 degrees, for a total tilt of 0 degrees. Here is the side view of the same car. The cabins are sized so that a heavy lift launch vehicle could put at least one 12-meter cabin in orbit. 2 12-meter cabins can be docked together to create a 24-meter cabin. By comparison, the ISS Destiny module is 4.3 meters in diameter and 8.5 meters long, so it could fit inside the space shuttle. This slide shows a perspective of a hypergravity vehicle car tilted at 30 degrees in addition to the 30-degree track superelevation. This is the 2G hypergravity configuration. The interiors of the cabins can be customized with the requirement that a passageway exists from one end to the other. This cabin shows a 6-room configuration. This image shows the top view of the tilt mechanism. A number of tilt mechanisms are feasible, but this design uses 4 scissor jacks per car as shown. The main idea here is that a servo motor simultaneously raises 2 jacks on one side while lowering the other jacks on the other side to control the cabin tilt. This slide shows the side view of the tilt mechanism. Each chassis rests on two-wheel trucks, which roll along the rails. Each wheel truck has electric motors to provide the locomotion. Each truck is slightly angled to follow the circular track. This brief animation puts all these pieces together. A 300-meter diameter track banked 30 degrees with a one-car, single-cabin hypergravity vehicle is shown. The cabin is banked negative 30 degrees when stopped to offset the track bank, keeping the cabin interior level. As the vehicle accelerates to its maximum velocity, the cabin tilts from negative 30 degrees to positive 30 degrees, according to the vehicle velocity, so that down is always straight down from the perspective of the cabin occupants. The vehicle is now at maximum velocity of 3.2 RPM, and the cabin is subject to 2 Gs. Now as the hypergravity vehicle slows down, the cabin tilts back from positive 30 degrees to negative 30 degrees, carefully matching the velocity, so the cabin contents remain level, with the exception of the effect caused by the vehicle decelerating, which can be reduced by decelerating over a longer period. The same phenomenon can occur on an aircraft when the pilot carefully matches the aircraft's bank angle with its turn rate, so that the passengers can't tell that the aircraft is turning if they don't look out the window. An aircraft can do this for minutes or even hours, but this hypergravity vehicle is designed to continuously generate hypergravity for years because that is how long it's going to take to understand the long-term effects of artificial gravity. In the short term, microgravity doesn't cause much harm. It's not until a person, animal, or plant experiences it for extended periods are the negative effects revealed. On the Moon or Mars, the negative effects may be less or may just take longer for them to manifest. That is one of the reasons why studying the long-term effects of artificial gravity is so important. This top view of the hypergravity vehicle shows a configuration where the cars form a complete ring. In this configuration, a person can walk around inside the entire hypergravity vehicle. The transfer vehicle is also shown aligning itself for transfer, while both are at operating velocity. The transfer vehicle is a single car that transfers people and cargo between the depot and the hypergravity vehicle as needed, so the hypergravity vehicle doesn't need to stop, which would reduce its gravity level back to 1 G. The transfer vehicle stops at the depot, unloads any people and cargo on board that left the hypergravity vehicle, then loads people and cargo headed for the hypergravity vehicle. The transfer vehicle then departs the depot, matches its velocity with the hypergravity vehicle, and then docks with the hypergravity vehicle. The people and cargo move from the transfer vehicle to the hypergravity vehicle. Once the transfer vehicle has emptied, people and cargo on the hypergravity vehicle bound for the depot enter the transfer vehicle. The transfer vehicle then undocks and then heads for the depot. This process repeats as needed. This view depicts the top view of a retractable passageway, similar to an aircraft jetway, for transfer of people and cargo. There are a couple ways to implement the transfer vehicle depending on how flexible the users want the overall system. If the system requirement is to support level transfers at any operating velocity, then the transfer vehicle must be able to raise and lower the transfer vehicle cabin as shown. On the left side of the slide, the transfer is at 2 G, while on the right side, the transfer is shown with both vehicles stopped. In both cases, the transfers are level from the perspective of the occupants. This slide shows the side view of the transfer vehicle with its cabin raised and lowered. If the system was designed only for level transfer at a specific velocity and gravity, then this design is suitable. The transfer vehicle cabin doesn't need to be raised and lowered. In an emergency, stairs may be necessary for transfer at other velocities. A hypergravity vehicle can have 2-story cabins as shown, doubling its capacity. Also shown, a hypergravity vehicle can operate in tunnels on Earth and potentially elsewhere. This slide shows a subset of the design trades made. For this design, a 300-meter diameter track with a 30-degree super elevation was selected as shown by the 3 blue rows. At 112 miles per hour, the hypergravity vehicle will be traveling at 3.2 RPMs, require an additional 30 degrees of tilt, and produce 1.97 Gs, including Earth's gravity. But but at half the velocity it only produces 1.09 Gs. Larger diameter tracks require the hypergravity vehicle to run much faster for the same gravity level, and smaller diameter tracks require higher RPM for the same gravity, which raises its own set of issues. It appears that most people can adjust to 3.2 RPMs and not be conscious of the fact that they are going in circles. However, the long-term effect of rotation on life is not well understood and is one of the purposes of this facility. Future variations of this facility could be built beyond Earth. Here are some examples of what would be needed to create 1G at different locations and vehicle ring diameters. Another consideration taken into account when selecting the 300-meter track diameter is the cabin hypergravity map. Within each car, the hypergravity varies, as shown in the slide, with the highest hypergravity in the two outer corners and the lowest hypergravity at the center of the cabin side closest to the track's circle center, because it is the closest point to the center. In this case, the maximum minimum gravity difference is 17 thousandths of a G. When selecting the cabin pitch angle, this design uses the cabin center as the cabin point for which it is level for the vehicle velocity. Other points will have a pitch up to about 1/2 of a degree as shown by this map. For a smaller track, the gravity pitch differences between points are more significant. Using the same cabins, much larger hypergravity vehicle cars can be assembled as needed. Shown as a 26 cabin car. However, the chassis and tilt mechanisms required, as well as the track gauge, are more substantial than those for the 1 or 2 cabin cars previously shown. These two perspective views show the 26 cabin hypergravity vehicle stopped at a negative 30-degree cabin tilt, which zeroes the 30-degree track superelevation, and a 30-degree pitch for 2G hypergravity. Although I don't expect a hypergravity vehicle to be used as a cruise ship, I suppose it could be used as an extraordinary fitness spa for people to lose weight and tone up without actually having to do exercises. A 26-cabin hypergravity vehicle could support 48 people at cruise ship population densities. Shown are 5 large cruise ships and their densities. 10 years ago, the Freedom of the Seas was the largest cruise ship, but there are much larger ones now. Just as the single cabin cars can be linked end-to-end around the entire track, so can the 26 cabin cars. 36 such cars fit on a 315-meter diameter track as shown. At this size, 4-meter wide spokes provide passageways for people and cargo to travel to and from the rotating center hub instead of using a transfer vehicle. The deck area of the hypergravity vehicle shown is still only 29% of the deck area of the Freedom of the Seas cruise ship. We know how to build ships this size. The extended Say hypergravity facility is the same diameter as the length of the USS Enterprise, which was launched in 1960, as shown in the slide. We can do this. The design also supports configuring the 26 cabin cars into 3 rings, doubling the car count to 72, also doubling its capacity. This supports the simultaneous generation of 3 significantly different hypergravity levels to better understand the effects of living with changing gravity levels. This side view of the 3-ring 72-car hypergravity vehicle shows each ring diameter and their associated hypergravity levels of 1.15 G, 1.5 G, and 1.96 G. Also shown is the hub elevator and tunnel for transfer of people and cargo from the hub to the depot and outside the facility. This illustrates the entire facility covered like a stadium, with an external rail spur to transfer cars to and from the facility. The whole facility could be underground instead. I've shown you what the fully populated facility looks like, but there are many smaller configurations that can be incrementally implemented. Here is an I configuration consisting of 2 to 10 26 cabin cars. Here's a similar Y configuration consisting of 3 to 15 cars. In space, the Y configuration is more stable than the I configuration if it is to be used as an analog. It turns out that the 72-car fully populated vehicle is essentially two Y configuration vehicles joined at the hub and rotated 180 degrees. Here is an X configuration. It is essentially two I configuration vehicles joined at the hub. The take-home message here is that the same cabins and cars can be used to create a wide variety of artificial gravity settlement configurations. There are several concepts of operations for this facility, ranging from unoccupied short-term operation to continuous operation with very long-term tours of duty for people. Finally, NASA does recognize the need to study artificial gravity and that ground analogs should be created. I don't know of anything as ambitious as what I have proposed that is being considered, but something like this should be. So to briefly recap, permanently extending life beyond Earth is important, urgent, and hard. Sooner or later, the survival of all known life will depend on this. While species are going extinct at an increasing rate, and we don't even know if permanently establishing life beyond Earth is possible. The three main immediately challenges appear to be gravity, radiation, and atmosphere, but maintaining a sustainable biome may be the greatest challenge for self-sufficiency. An extensible, modular, extended-stay hypergravity facility design concept as a ground analog for a space settlement was presented that can be used to address all four challenges. Such a facility can test what we fly, and is the next practical step to permanently extend life beyond Earth. We can do this, and can start now. The paper this talk was based on can be downloaded at this link, Ad Astra.